Good afternoon, everyone. I'm Xue Jiang from the Technical University of Munich, and it's a pleasure for me to be here today to present our work on distributed GAN-based privacy-preserving publication of vertically partitioned data. This is a joint work with my colleagues Xue Jiang, Xue and Jens Grosskloks. So we know that in the era of big data, large and diverse quantities of personal data are frequently collected by different companies and institutes for data mining and building AI services. And usually, different institutes may have interest in different user attributes. For instance, an e-commerce company would like to collect a user's shopping history for purchase recommendation, while a bank tends to analyze users' financial data to detect money laundering. And in some scenarios, a third-party company would like to gather information from various sources to develop improved AI models. For instance, in the previous example, a credit card company would like to use the attributes from both parties to gain a better understanding of the user behaviors and to develop a more accurate credit assessment model. However, since this local dataset usually contains sensitive information of individual users, the direct publication of this data may lead to serious privacy leakage. And in recent decades, differential privacy has been considered a state-of-the-art technique for privacy-preserving data publication. The main idea is to apply several randomized mechanisms on the original dataset so that the attacker cannot infer sensitive information of a single record from the privatized output. Here, the epsilon in the definition refers to the privacy budget. The smaller epsilon, the harder the attacker can distinguish two neighboring datasets and the stronger privacy. So for publishing the vertically partitioned data with CP guarantees, existing statistics-based works propose to privately compute the multivariate distributions of all the local attributes and publish these privatized distributions to the server to generate a joint synthetic dataset. However, since the privacy budget here is evenly divided and allocated to all the attribute pairs, this kind of methods may suffer from large utility loss with the increase of data dimensionality and domain size. And considering the extraordinary performance of deep generative models, such as autoencoders and GANs in synthesizing high-dimensional datasets, we wonder whether we can use such kind of models for publishing vertically partitioned data with better utility. However, conducting data synthesis in the vertical setting still faces several challenges. First of all, since we assume that the real data are located on the local side and cannot be directly accessed by the server, we cannot train the generative models as if in the centralized setting. Also, since in the vertical setting, all the local parties have different attribute sets, it is difficult for us to apply the same model structure on all the local data sets. And thirdly, we must consider privacy protection to prevent potential privacy leakage from the trained generative models and synthetic data. And to address the above challenges, in this paper, we propose Vertigan, the first GAN-based framework for publishing vertically partitioned data with differential privacy. In contrast to the previous statistic-based methods, our framework directly employs a GAN model to learn the distribution of local datasets and to generate high-utility synthetic data on the server side. And to start with, we took advantage of GAN's separate generator discriminator structure to address the data inaccessibility and attribute inconsistency problem. More specifically, our framework incorporates a global generator on the server side and multiple independent discriminators on the local side. And the structure of each local discriminator complies with the respective local attribute set. During training, the server will broadcast the current global generator to the local side, and each party uses the generator to produce synthetic data for training the local discriminator and to compute the generator's gradient. Then this generator's gradient will be returned to the server side for updating the global model parameters. By using this distributed training strategy, this server can achieve to train the generator without a direct access to the local datasets. And the using of multiple independent local discriminator effectively addresses the attribute inconsistency problem. We further apply a number of modifications to improve the utility and privacy of our framework. First, we adopt a multi-output structure for the global generator to better capture the cross-attribute correlations among local parties. The generator contains a number of common layers followed by several separate branches. Given this batch of random inputs, all the branches synchronously output different attributes values of the same batch of syntactic records, and the concatenation of all the outputs forms the joint syntactic dataset. Then during training, each local party only needs to use syntactic data from one branch to train the local discriminator and to compute the generator's gradient. After aggregating the generator's gradient at the server side, we observe that the parameters of each branch are updated actually based on the gradient sent from one specific local party, while the parameters of the common layers are actually updated based on the gradients of all the local parties. This enables the generator to effectively capture attribute correlations within and among local parties. Also recall that in the vertical setting, different local parties may have an attribute set of the same batch of records. We apply a pseudo-random number generator for aligning the training data. Given the same random seed, it can produce the same sequence of indices for selecting the real data and the same batch of random inputs for generating the syntactic data, which enables the data from all the local parties be record-wise aligned during training. And finally, we apply gradient perturbation when training the local discriminator to ensure the model satisfies epsilon delta differential privacy for the local dataset. And according to DP's post-processing property, the gradients computed by the discriminator also satisfies epsilon delta DP guarantee, which prevents potential privacy leakage from the generative model and the synthetic data. After training, the server can directly use the generator to generate joint syntactic dataset at the server side, which will be used for downstream AI training and data mining tasks. We evaluate the utility and privacy of our framework using 6 open source datasets and compare the performance of framework with 2 statistics-based baseline algorithms. So first, we investigate whether the syntactic data can preserve similar statistical properties as real data. And here we first use the average total variation distance to compare the difference of multivariate distributions between real and synthetic data. The lower AVD, the closer the two distributions and the better data utility. And from the results, it can be seen that the synthetic data generated by our framework generally achieves a smaller AVD compared to the baseline algorithms and shows more improvement for datasets with larger domains, which indicates that our framework is more capable of capturing the multivariate distributions of high-dimensional datasets. And we further visualize the correlation heat maps of real and synthetic data to analyze the cross-attribute correlations. From the results, it can be seen that the synthetic data has very similar correlations to real data, which again demonstrates that the synthetic data generated by our framework can well preserve the statistical properties of real data. Next, we investigate the utility of synthetic data in AI training tasks. To this end, we respectively train two classifiers with real and synthetic data and test both models with a set of held-out real dataset. And the results shown here is the test accuracy of models trained with real data and synthetic data with different privacy levels. It can be seen that our framework consistently achieves a better test accuracy compared to the baseline algorithms. With epsilon equals to 8, we can achieve around 2 to 15% of accuracy improvement, which indicates that the synthetic data generated by our framework can effectively support AI training tasks. Finally, we empirically evaluate the privacy protection capability of our framework using a black box membership inference attack, where an attacker aims to use the synthetic dataset to infer whether a target data was used in the training data. So given a target record, the attacker computes the ratio of synthetic record falls within its neighborhood. The higher the ratio, the more likely the data was used for training the generator. From the result, it can be seen that synthetic data generated without protection still has relatively high privacy risk. For census and Twitter datasets, we can even have 65% of attack accuracy. In contrast, applying differential privacy can effectively reduce the privacy risk and to provide enhanced privacy protection to local dataset. So in conclusion, in this paper, we proposed the Vertigan, the first GAN-based framework for publishing vertically partitioned data, which significantly outperforms the baseline algorithms, and the synthetic data can effectively support downstream data mining at AI training tasks. Thank you.
Thank you for the talk. As I said earlier, please use the Zulip application for any questions. We have already some questions, so we have a question from Mohammed, who is asking, why is it important for different parties to get the same seed in your system?
For different parties to get the same seed?
Yes.
In the same seed. Because when we train the generative models, we want different parties. We want the discriminator and the generator to learn the entire cross-attribute correlations of a single record. But actually, different parties have different parts of the attribute sets. Then that's why we need the same seed to align all the real data and synthetic data in order to let the model to learn these cross-attribute correlations.
Thank you. Then we have another question from Teresa, who is asking, how do you choose the hyperparameters for the DP training, such as the sensitivity?
The sensitivity is actually chosen by the clipping bound. If some of you may know that for gradient perturbation, usually we first clip the gradient and then add a certain number of noise based on this clipping bound. And this clipping bound actually is the sensitivity we defined to bound this sensitive gradients.
Thank you. And another question from Valentin. You touched upon this, but could you elaborate on why the generator learns correlations across the different parties? The local discriminators only have access to the attributes local to each party, but not to those of the other parties, right?
Sorry.
So he's saying, why does the generator learn correlations among the parties?
Okay. So from the previous slides, we show that if we take a look at the aggregated generator's gradient, it can be seen that the generator, this gradient can be divided into two parts, one for the branches and one for the common layers. And for the branches, it is based on the gradient from one local party computed by the discriminator. And for the common layer, it's actually aggregated gradients from all the local parties. And this contains the information of the data set across different local parties.
Okay, thank you. Let's thank the speaker again for her nice talk.